studied the density property of real numbers and order properties of real numbers, we are now in a position to define the real numbers between any two values. That is, the intervals we can define on the set of all real numbers, which can be considered as the set of all real numbers between any two real numbers. So, the order property ensures that the real numbers can be arranged in an ascending or descending order in R. So, with that in mind, we can go to the definition of open interval. Let A B belongs to R with A is less than B. The open interval A B is the set of all real numbers which are between A and B. The points A and B are called the endpoints of the interval. So, the open interval consists of all those real numbers between any two given real numbers A and B, which are called the endpoints of R or endpoints of the interval. Whereas, if A and B are elements of R where A is less than B, the closed interval AB consists of all those elements X which are between A and B and including A and B. Here also these points A and B are called the endpoints of the interval. The intervals which include one of the endpoints and excludes the other are called the semi-open or semi-closed or half-open or half-closed intervals. Both the names can be seen in literature. They are called semi-closed or semi-open or half-closed or half-open intervals. So, looking at some examples, we can see open interval 0 to 1 consists of all those real numbers X such that 0 is strictly less than X less than 1, and the closed interval 0 to 1 is equal to the set of all real numbers which are less than or equal to 1 and less than or equal to, greater than or equal to 0. This interval is called the unit interval and it is denoted by standard notation capital I. So, capital I stands for the unit interval in the American standard notations. So, I is equal to the closed interval 0 to 1. Now, semi-closed intervals can be viewed as excluding 0 including 1, which can be defined as the set of all real numbers which are greater than 0, strictly greater than 0, but less than or equal to 1, and the closed 0, open 1, this is also a semi-open interval or semi-closed interval. We can consider this as the set of all real numbers for which 0 less than or equal to X less than 1. So, these are called the half closed or half open intervals. These are some of the examples. So, in geometry, we can consider the open intervals as say open 0 to 1, the closed intervals as including 0 and including 1. This is the interval including 0 and including 1. So, this is 0, there is no gap here. Now, semi-closed intervals being open on one side, closed on the other, or it can be open on closed on this side and open on the right. For all these intervals, the endpoints are exactly the same, they are 0 and 1s. So, that is what we have seen in the definition. So, all these intervals that we have defined have the endpoints A and B itself. The endpoints are not going to change. Then, the intervals having endpoints, whatever be the nature of the interval, whether it is open or closed or semi-open or semi-closed, whatever it be, all the intervals having endpoints A and B are all bounded, the upper bound being B or any number greater than b. So, obviously, the supremum will be b and the infimum being a. And all the intervals are having endpoints a and b. So, the length of the interval is b minus a. For example, we can see the length of these intervals are all equal to 1. Why? Because they are having the endpoints as 0 and 1. So, the length of all the intervals that we have discussed so far is equal to 1 here. So, how did 1 get? B minus a. So, that is the length of these intervals, whether it is open interval or closed interval or semi-closed, every interval has length b minus a and these are bounded. Also, any subset of R means the null set as well as singleton set can also be represented in terms of intervals as follows. If the endpoints are the same, then the corresponding open interval AA determines the empty set and the closed interval AA determines the singleton set A. So, how does this happen is because of the definition of open interval. Supposing here B is equal to A, we have open interval AA is equal to the set of all x belonging to R for which A is less than x less than A. And we know that we have studied the order properties and we have been seeing it for a couple of sessions that none of the real numbers can satisfy this relation A less than x less than A. So, none of the real numbers x satisfies this condition because there is no equality here. So, A cannot be strictly less than x, strictly less than A. So, we arrive at the conclusion that such a set is empty. That is why we take open interval AA is equal to the null set. Whereas, if you define closed interval AA, by the definition, it is equal to the set of all real numbers for which A is strictly less than or equal to x less than or equal to, instead of B, you have A itself and that is equal to, so x can take a single value, and what is that single value which x can take? X can be equal to A because on both sides we have A itself. So, this is equal to the singleton set A because only the real number A satisfies the condition that A is less than or equal to x less than or equal to A. So, it is a singleton set A. So, that is why we can define the empty set phi as open interval AA and the singleton set A as the closed interval AA. Now, these are all examples of finite intervals that we were discussing so far, because we had an upper bound or supremum as B and a lower bound, say infimum as A. So, these were all finite intervals, but there are some intervals in the set of all real numbers which cannot be considered as finite. They are infinite intervals. Say for example, there are infinite open intervals which are also called open rays in some textbooks, like negative infinity up to B if you consider, that is defined as the set of all real numbers which are strictly less than B, and A to infinity if you consider, it is the set of all real numbers which are strictly greater than A. So, these are called infinite open intervals because they exclude the upper bounds and the lower bounds. So, this set minus infinity B if you consider, we can see by the definition of supremum, B is the supremum of this set, and does it have an infimum? No, because it is minus infinity on the left side. So, if x is less than B, the infinite ray is bounded above but not below, whereas this infinite interval, infinite open interval A to infinity which is defined as the set of all real numbers which are greater than a possess a lower bound but no upper bound. We can geometrically visualize this. Open interval minus infinity up to b can be considered as the entire real line with some point b here, this direction. So, from b it is an open ended, it is an open ray going to negative infinity, that is why it is called open ray. Or if we consider a to infinity, we can see that here it is a hole because b is excluded. And if we consider a to infinity, we can consider a somewhere here, it goes to infinity towards the right side. So, these are the visualizations of infinite intervals that we have discussed here. Now, these are infinite open intervals. So, what are infinite closed intervals? Which includes the supremum and the infimum. So, again if we visualize it, we can see that negative infinity closed b contains all the points starting from negative infinity up to b. So, this is the region which is considered, and closed a infinity is nothing but starting from a, it is going up to infinity. So, it is also included, that is why we are not putting a hole there, that is also included. So, these are examples or these are the definitions of infinite closed intervals. Now, how can we represent the entire set R as an interval? The entire set R starts from negative infinity, goes up to positive infinity. So, it can be considered as the infinite open interval, negative infinity up to infinity. So, this is the entire set R, infinite interval. So, it is unbounded as well. These are all unbounded because it does not have a lower bound, either a lower bound or an upper bound is not there. So, these are all unbounded intervals, whereas the entire set R is definitely an unbounded interval. So, having seen all these definitions of intervals, what makes a subset of R an interval? That is a question. So, that is answered by the characterization theorem, which says that if S is a subset of R that contains at least 2 points and possess the property that if x and y belongs to S and if x is less than y, then the closed interval x y is contained in S. So, this, if you look closely, you can see that suppose S is a non-empty subset of R which contains at least 2 points, that is why we are saying it is a non-empty subset. So, there should not be single point, there should be at least 2 points. And it has the property that for every x and y in S, if x is less than y, everything from x to y is swept inside S. That is what is meant by the closed interval x y is contained in S. Then truly S is an interval. So, that makes a set S an interval. That is why the name of the theorem is characterization theorem. See, for example, if we consider the set n of natural numbers, we can see that this is equal to 1, 2, 3, etc. So, we cannot say that the points between 1 and 2 is swept inside n. So, this is as such not an interval. That is why the set of all natural numbers and finite sets etc. cannot be considered as intervals, because the characterization theorem is not satisfied there. So, we consider the proof of this theorem, that is, we consider the proof of the characterization theorem. We are given S is a non-empty set which contains at least 2 points, and it has the property that if x is less than y, then the closed interval x y is contained in S. Okay. So, S is a non-empty set and x is less than y implies the closed interval xy is contained in S. Now, we have to show that S is an interval. So, we consider different cases. So, we are simply said that S not equal to phi is a subset of R, that is only condition given in the statement, and x is less than y implies the closed interval xy is contained in S. So, the proof consists of case 1. Suppose your S is bounded, then definitely S has an upper bound and a lower bound. So, S is not equal to phi subset of R with this condition ensures the existence of a supremum and an infimum because of the supremum property and infimum property. So, S is bounded indicates that there exists, say A is equal to infimum of S and B is equal to supremum of S. From where does it follow? It follows from the completeness property of R. Completeness property of R. So, we have an infimum of S and a supremum of S. Therefore, what we can say is S is fully contained inside the closed interval AB, because every element of S is bounded above by B and below by A. Therefore, S is contained fully inside the closed interval AB. Now, we have to prove, it is left to prove that open interval AB is contained in S, because we need to show that S is an interval only, whether it is a closed interval, open interval, whatever it be, we are not bothered. We have to simply show that S is an interval. So, we will show that we have now S is contained in closed interval AB. If we are successful in showing that open interval is contained in S, then definitely S becomes open interval AB. So, that is enough. So, let us take an Z element of open interval AB. Then what happens to this Z? Where is this Z between A and B? By the definition of open interval, Z belongs to open interval AB implies A less than Z less than B. So, since A is the infimum of S, Z is greater than A indicates that Z cannot be a lower bound. Z cannot be a lower bound. Why? Because the greatest lower bound is A, cannot be a lower bound. So, how can we show that a real number is not a lower bound of a set? There exists at least one element, say S1, such that Z is greater than S1. So, we have Z cannot be a lower bound means there is at least one element of the set S which is less than that number Z. Similarly, B is the supremum of S and Z is less than B indicates that Z cannot be an upper bound of the set S. Therefore, there exists some S2 element of S such that Z is less than S2. So, now we have found two elements of the set S such that therefore, we have two elements S1 and S2 in S such that S1 is less than Z less than S2. And by the property that is given in the statement, if you have two numbers S1 and S2 such that S1 is less than S2, the interval S1 S2 is contained fully inside S. So, Z is one of the points in this interval, which implies Z is an element of S. Therefore, Z being an arbitrary element between A and B, open interval AB is fully contained inside S. So, thus we have shown that S is equal to open interval AB. So, S is equal to open interval AB. If S contains both the supremum and infimum, S becomes the closed interval AB. If it contains at least one of the infimum or supremum, it becomes a semi-closed interval. But anyway, S is an interval now. Now, we consider case 2. S is bounded above only. So, S becomes a non-empty subset which is bounded above. So, that ensures S has a supremum in R. Therefore, S is contained fully inside minus infinity up to B. Now, the similar arguments can be applied to show that negative infinity B is contained inside S as well, because a similar argument like that we have done just now shows that this is contained in S, because if we take an Z element of negative infinity up to B, then since Z is less than B, Z cannot be an upper bound, because the least upper bound is B. Therefore, there exists an S1 in S such that S1 is greater than Z. Okay. Therefore, where is your S1 now? It is between, so minus infinity B is contained in S, because we can also have minus infinity is the least value. Therefore, there exists no lower bound. Therefore, there exists some S2 such that S2 is larger than, Z is greater than S2, because if Z is larger, if Z is lesser than any of the sets of any element of the set S, Z becomes a lower bound. But because the set S is not bounded from below, there cannot exist such a lower bound. So, Z cannot be a lower bound. That ensures that definitely there exists an S2 element of S such that Z is greater than S2. So, the similar argument as in the previous case can be applied here also. S1, S2, the interval is swept inside S, therefore, Z is contained inside S. So, we can show that because the set S is not bounded from below, and since B is an upper bound, this is satisfied. Therefore, in this case we have S is equal to negative infinity up to B. The other cases can also be proved similarly. So, that shows the property that if x and y belongs to the set S with x less than y, then this closed interval x y is fully contained inside S, then S is an interval. Now, we can look at an interesting result which was proved by Cantor. To prove the uncountability of R, he has proved the uncountability of the interval 0, 1. So, the Cantor's proof says that the unit interval closed interval 0, 1 is not countable. So, the proof is by taking the decimal representations of the elements of the set 0, 1 and finally creating a new element having a decimal representation which is not one of the elements, not one among the ones listed in the sequence. So, the proof of uncountability of R using the uncountability of 0, 1 was done by Cantor, and that shows the importance of unit intervals as well as intervals in the real number system. So, literally speaking, a very small interval which is closed interval 0, 1 which seems to be countable is again uncountable. That shows the power of the set of all real numbers which are uncountable, and that is the importance of intervals as well. Thank you.